This video is for section 2.8, which is the last section in chapter 2. I'll split this into two separate videos with two separate quizzes. I encourage you to read through the examples in the section. They start on page 128. So the general idea here is that we're going to have an equation and we want to break it down using the roots. Okay? So let's take a look at problem 2 on page 132. So, problem 2 says 3x cubed minus 5x squared plus 2x minus 8 equals 0. So the instructions say find all the real and complex roots for the given equation, and then express the given polynomial as the product of prime factors with integer coefficients. So we're going to factor this as well. Okay, so we're going to find the roots, and we're also going to factor the polynomial. So the first thing that we want to do, just like we've done in most of these problems throughout chapter 2, is to graph this. Okay, so let's take a look at what the graph looks like. 3x cubed minus 5x squared plus 2x minus 8. And we'll look at this in the standard window. And then we'll find whatever roots we can see. So here's what it looks like on the graphing calculator. And you can see a root there. It looks like it's at positive 2. Again, we can go into the table by hitting second graph. And there's our table. And you can see when x is positive 2, y is 0. So we know that 2 is a root. We actually don't really have to go through the process of using that root finder. So we know that x equals 2 is a root. Okay. So let's go ahead and write that down. If we know that x equals 2 is a root, that means that x minus 2 must be a factor. Okay, so this is where that section 2.5 that we talked about previously comes in handy. Okay, now to find this missing factor, what we have to do is divide this polynomial by this factor right here, and that'll tell us the missing piece. So that's why we have the synthetic division. So let's take our coefficients here, 3 minus 5, 2 and minus 8, and we're going to do the synthetic division with a positive 2. And notice that the sign in the factor is always the opposite of the sign for the root and the number that we use in the synthetic division. All right, so let's see here. 3 comes straight down. That'll be 6, 1, 4, 8. And if this is a root that you get off the graph, then this will always have a 0 remainder. If you don't get a 0 remainder when you're dividing this by something that you know happens to be a root, then you've made a mistake somewhere. Okay, so this is going to be 3x squared plus 1x plus 4 is our missing factor. And the reason why we didn't see any additional roots on the graph is because this polynomial has complex roots. So if we run this through the quadratic, right, we set this equal to 0. We can do the same thing with this factor, set it equal to 0, and then run it through the quadratic. And there are complex roots. X is negative 1/6 plus or minus 1.143i. Okay, so I mentioned the fundamental theorem of algebra when we were talking about some earlier concepts in this chapter. The fundamental theorem of algebra says that you can have as many roots as the highest power of x in the equation. Okay, so this is an x to the third power. Here's our 3 roots. Okay. Now, occasionally we might get what's called a repeated root, and I'll talk about that when we run into it. Okay, so there's problem number 2. Let's look at problem number 4. Okay, so problem number 4 is a 4th degree equation. So we've got x to the 4th plus x cubed minus 3x squared minus 17x minus 30 equals 0. All right, so again, first thing we want to do here is go ahead and graph our polynomial. Minus 3x squared minus 17x minus 30. Okay. And then I'll show you what the screen looks like for this polynomial. Let's see here. Get it to focus. So there's the graph. It looks like we've got roots at positive 3 and negative 2. And again, if you want to find out if it looks like whole number roots, go look in the table. Okay? And so we'll hit second graph, and that'll bring up the table. Let's see. There we go. And yeah, you can see at negative 2, y is 0. At positive 3, y is 0. Okay. So now we've got 2 whole number roots. Let's see here. One root at negative 2, the other root at positive 3. Okay, so that means that x plus 2 is a factor, and x minus 3 is also a factor. Now we're going to have a missing factor here. To find out what this is, we're going to divide this thing by both of these. Both of these binomials, we're going to use these roots in the synthetic division, and we're going to do it twice. Okay? So first we'll pick off the coefficients from our polynomial. 1, 1, minus 3, minus 17, and minus 30. And let's see, it doesn't matter which one we start with. I'll start with the 3. Okay, so that'll be 1, 4, 9, 12, minus 5. And let's see here, did I make a mistake somewhere? Let's see here. 3 minus 17, 30, 3, 4, 12, 9. Ah, there it is. I added 3 plus 9 and got 12. And I knew that this was, so how did I know I made a mistake? Well, if I continued, I don't get a 0 remainder. Okay? And that's what I was saying. If this is a root, and you know it's a root from the graph, then you should get a 0 remainder. So that's how I saw that I had made a mistake here. So 9 times 3 is 27. There we go. 27 minus 17 is 10. 10 times 3 is 30. And there's our 0 remainder. Okay, now we're going to do this again, and this time we're going to divide using, we're going to do the synthetic division using that negative 2. So, negative 2, negative 4, negative 10. And there we go. So, our missing factor is x squared plus 2x plus 5. And we can set this last factor equal to 0. And then run it through the quadratic. Let's see here. So 1, 2, and 5. And this gives us x equals negative 1 plus or minus 2i. And so this is a 4th degree equation. 1, 2, 3, 4 roots. Okay? This is 2 roots. This is negative 1 plus 2i and negative 1 minus 2i. All right, so let's see, that's problem 4. Let's take a look at problem 8. So problem 8 is where we run into this idea of repeated roots. So before we start that, let me just talk a little bit about it. And we saw this when we were talking about quadratic equations. I used these examples. Let's see, what was it? X squared minus 6x plus 3 looks something like this and has roots here and here. All right, and then x squared minus 6x plus 9 just comes down and touches and goes back up. And we were doing this in the section where we were talking about complex roots, because when we get to this right here, that's saying that the equation x squared minus 6x plus 12 equals 0 has complex roots. This would have two real roots. So this one has a single repeated root, because if you take x squared minus 6x plus 9 equals 0, it factors as x minus 3 times x minus 3. So it does, I guess, have two roots, but it's the same root twice. Okay? And what it looks like on the graph is where it just comes down and touches and then goes back up again. Right? So this one will cross in two different places. This one won't cross the x-axis at all because its roots are complex. All right, so in problem 8, and I'm going to do problem 7 as an example in a minute as well, and we'll see this, all right? That's the sort of indication that you've got a repeated root. All right, so problem 8. Let's see here. This one is also fourth degree, so x to the fourth plus 4x cubed plus 2x squared plus 12x plus 45 equals 0. All right, so let's get this graphed. Let's see. X to the fourth, 4x cubed, 2x squared plus 12x plus 45. Okay, let's see what this looks like. Okay, so all we see in this one is that graph. It comes down and it touches right over here. It looks like -3. And again, we can go into the table. If we hit second graph, there's the table. And yeah, you can see at -3, y is equal to 0. Okay? But that's the only root that we see on there. We don't see any other roots. Now, I have set these up so that there isn't anything happening out past +10 or out past -10. Okay? There are ways to determine whether or not there are other roots outside of this window. But all we can see here is the root at -3. So, let's get this to focus. There we go. So we're going to use that root of -3. And the way that the graph comes down and touches and goes back up is a hint that this -3 is a repeated root. Okay? So, now the real guarantee that it's a repeated root is if we divide it into this twice and get 0 remainders each time. That's how we know for sure that this -3 is a repeated root. So let's do the synthetic division. We'll put our coefficients up there. -3, 15, -45. There's our 0 remainder. Okay? Now, let's do it again. -3, -2, 6, 5, -15. There's our 0 remainder. Okay, so now we know that we've got a double root at x equals -3. So that means we have 2 factors of x plus 3. Now, how do we know that it's not repeated a third time? Well, there's a couple ways, okay? One is that if it's repeated an even number of times, it'll do that. If it's repeated an odd number of times, it'll do something like this. It'll flatten out as it's passing through the root, okay? The other thing you can do is try it one more time. Do the synthetic division with this -3 again, and notice we don't get a 0 remainder. Okay, so a couple different ways to tell how many times the root is being repeated. This is our missing factor, x squared minus 2x plus 5. And so we can set that equal to 0. And then run it through the quadratic formula. 1 minus 2 and 5, and that gives us 1 plus 2i and 1 minus 3i. So really there's only 3 distinct roots, but this is repeated twice, and that's a part of the factorization. That comes from the fact that it has this repeated factor of x plus 3. You could also write this factorization x plus 3 squared times x squared minus 2x plus 5. There's nothing wrong with that. That says the same thing that this does. So in terms of answers for these questions, what I'm looking for is the roots and the factorization. Okay? All right. Now let's go back and look at problem 7. Normally I do the even problems as examples, but 7 is a good example for some of the other problems that come up in this section. So let's take a look at that. All right, problem 7. Oh, this is a 5th degree equation, so we could have up to 5 roots on this. 9x to the 4th, 31x cubed, 49x squared, 36x minus 10. Okay, so again, first thing we want to do is graph this. So that'll be x to the 5th minus 9x to the 4th plus 31x cubed minus 49x squared 36x minus 10. Okay, so let's see what the graph looks like here. Let's see here. X to the 5th. Oh, I typed this in wrong. And I noticed because I didn't get any whole number roots on here. So let's put that, fix that, and then we'll look at the graph. And so again, that's a perfect example of what I keep saying is double check what you've typed in. Okay. All right. So here's what the graph for number 7 looks like. And there it is. And hopefully you can see right here as it's passing through positive 1, you can see how the graph flattens out a little bit. And so we can go in there and look in the table at positive 1. What's happening? Yeah, when x is positive 1, y is equal to 0. Okay, so we know that we've got a root at positive 1. That's the only root that we can see on here. So we'll just start with that. X equals 1. So we know that x minus 1 is going to be a factor. All right, so let's see here. 1 minus 9, 31 minus 49, 36 minus 10. Okay, so we'll use the 1 for the synthetic division. Let's see here. 23, so that'll be minus 26, positive 10, and 0 remainder. Okay? Because if it's a root, that means that this factor has to divide evenly into that original polynomial. Well, we didn't see any other roots on the graph. So let's just try one again. All right? And the way that it was flattening out as it passed through there like this, okay, that's a hint that you've got a root that's going to be repeated, like I said, an odd number of times. So let's run it through the synthetic division one more time. And there it is, another 0 remainder. And that's only twice, right? This says that it should be an odd number of times, so let's try this one more time. And there it is. So this is a triple root, okay? You could just put a cubed up there if you want, or you can list each of these factors out individually, okay? So these 3 divisions with 0 remainders indicate that positive 1 is a triple root, all right? And our missing factor is our last answer right here, x squared minus 6x plus 10. So we set that equal to 0, and then we can run it through the quadratic formula. Let's see here. And we get x equals 3 plus or minus I. So there's 2 roots here, and we've got 3 of these repeated roots. I mean, really, it's just one other distinct root. But because of the way that the factors work out, we consider that to be an extra 3 roots. And so again, you can write your factorization like this. You can also write it as x minus 1 to the 3rd times x squared minus 6x plus 10. Either way is fine. Okay, so I think that's a good introduction to section 2.8. And these are good examples for doing all those problems in what I've labeled set number 1 there. In the next video, we'll look at set number 2 and talk about how to do those problems.